Good morning. This is Rajshri S, Assistant Professor, Department of Mathematics, Government Science College, Autonomous, Bengaluru. Today's topic for session 1 is Leibniz rule of products for nth derivative. So let's start with the statement. This is the statement of Leibniz theorem. If y is equal to u into v, where u is equal to function of x and v equal to function of x, then nth derivative of uv is equal to u into vn plus nc1 u1 vn minus 1 plus nc2 u2 vn minus 2 plus nc3 u3 vn minus 3 etc. ncr ur vn minus r plus unv. See here, this vn is nothing but the nth derivative of v, and this un is nothing but the nth derivative of u, and this n minus 1 vn minus 1 is n minus 1th derivative of v, and so on. So this is what I have mentioned here. Okay, this is nothing but the nth derivative of uv, this one. So let's move on to the proof. And we are proving this statement using principle of mathematical induction. Step 1. To prove that the result is true for n equal to 1 and 2. For n equal to 1, LHS is equal to uv of 1. See here, for n equal to 1, what I did is, I've just replaced n by 1 here. This is LHS. uv of 1 is LHS. And RHS is uv1 plus 1c1 u1 v1 minus 1. That is v0. v0 means zeroth derivative of v. Zeroth derivative of v is v itself. And there will be no next terms because that becomes 1c2, which doesn't exist. So there are only two terms on the RHS. So that is what I have written here. LHS is equal to uv1. What is uv1? It is first derivative of uv. So I have just differentiated this with using a product rule. So I have differentiated u, so that is u1, and I've kept v silent, plus I've kept u silent and differentiated v here. So it is u1v plus uv1. And here, this is uv1. I just told here uv1 plus 1c1 u1 v0. So that is what I have written here, equal to, see, this is nothing but the combination, and the definition of combination I have written it here. NCR is equal to n factorial by r factorial into n minus r factorial. And here this n, actually this r cannot be greater than n. It can be less than or equal to n. At most it can be equal to n, but it can't be greater than n. So that is why I have stopped here. There is no 1c2 here, because it can't, that r can't cross the limit of this n. So there exists only two terms on RHS, and 1c1 using this formula, it is 1 factorial by 1 factorial into 1 minus 1 factorial. 0 factorial is 1. So here the value of 1c1 using this definition will be 1. So it is uv1 plus u1. v0 is just v, that is 0th derivative of v is v. See, you can just compare these two, LHS and this is RHS, both are same. So what I'm doing is, since LHS equal to RHS, the result is true for n equal to 1. So we have checked the result for n equal to 1, and it is the statement holds for n equal to 1. Let's move on to n equal to 2. So here what I'm doing is, I'm replacing n by 2 here. So what is the LHS? uv2, that is second derivative of uv is LHS, and RHS will be, say this I have written here, uv2. And we know uv1. What is uv1? I have written it here. uv1 is here. So differentiating this once again, you will get uv2. So differentiating this, you will get uv2. Okay. So I have just used product rule for these terms. So here it is u1 into differentiation of this v is v1 plus, I'm keeping this silent, differentiating this, you'll get u2 into v plus, differentiating this and keeping this silent, u1 v1 plus, keeping this silent and differentiating this, you'll get u v2. So there are two terms of this u1 v1. So I have written 2 u1 v1, and remaining terms I have written as it is. u2v plus 2 u1 v1 plus uv2 is LHS part. Let's move on to RHS. Yes, this is LHS. I'm just replacing n by 2 here. So it is uv2 plus 1c, this is 2c1 u1 v2 minus 1 plus 2c2 u2 v2 minus 2. So this is what I have written here, and using the definition of combination, 2c1 is nothing but 2. That is 2 factorial by 1 factorial into 1 factorial will be 2, and 2c naught is nothing but 1. That is 2 factorial by 0 factorial into 2 minus 0 factorial is 2 factorial. So at last you will get 2 factorial by 2 factorial, and that is nothing but 1. So this is uv2 and this is 2 u1 v1 and this is 1 u2v. So you can just compare these two. These two are looking same. Okay, see this uv2 is here and this u2v is here, and this is 2 u1 v1 and that is here. And here, you can compare these two. LHS is equal to RHS. Therefore, the result is true for n equal to 2 also. And next step in mathematical induction is we'll assume that the result is true for n equal to m. Step 2 is we'll assume that the result is true for n equal to m. So here I just replace n by m. That's it. This is for n. If the result is true for n equal to m, then I'll be replacing this n by m. So this is what I have written here. Assumption of the result for n equal to m is so much. And I'll name this equation as 1. Equation 1. Okay. And here I have written this extra term. That's it here. You will be getting MCR UR V minus V M minus R. Previous term of that will be MCR minus 1 because the previous term of this. Next term will be R plus 1. And UR minus 1 VM minus R plus 1. So this is what I have written here. And here also I have written this previous term. MC M minus 1 because the previous term. UM minus 1 V1. Okay. Yeah, one hint I like to give is when you add this, when you add m minus um minus 1 v1, you'll be getting m. See, wherever you do here, see here u0 vm, 0 plus m is m, and here it is 1 plus m minus 1 is m, 2 plus m minus 2 is m. So you can just check or verify like that whether you have written correctly or not. Okay. And here let's move to step 3. What is that step 3? We should prove that the result is true for n equal to m plus 1. In the previous step, we have assumed that the result is true for n equal to m. In this step, we have to prove that the result is true for n equal to m plus 1. That is, what we should prove? We should prove that uv m plus 1 is equal to so much. See, this what I've done is, I've just replaced m by m plus 1 here. Okay, I've just replaced m by m plus 1. So you'll get so much. See here I have replaced m by m plus 1. This is what I'll get, and same thing with the remaining terms also. Okay, fine. So actually we should prove this. Okay, we should prove this using this step 2. We should prove this step 3. So how will you use this step 2? We have UVM and we want UVM plus 1. So how are we getting that? When you differentiate this with respect to x once again, you will get UVM plus 1. So that is what I have done here. Yeah. Differentiating 1 with respect to x, we get UVM plus 1. Okay, see, I'll just slide this. See, when you differentiate this using product rule, u v n plus 1, yes, u v n plus 1 plus, keeping this silent, differentiating this, you will have u1 vm. u1 vm is here. So this is all about the product rule for the first term. This term I have differentiated, that's it. And when you differentiate the second term, see this mc1 is constant, you'll keep this outside and differentiate u1 vm minus 1. Again you are using the product rule for this u1 vm minus 1. So when you differentiate this u1, you keep this silent first and then differentiate this. vm minus 1 plus 1 is just m. So it is u1 vm. So it is u1 vm. Next, when you differentiate this, you're keeping this silent and differentiating this, you have u2 vm minus 1. So it is u2 vm minus 1. So I have kept this constant outside and I have differentiated that using product rule. So the next term is mc2 u2 vm minus 2, this one. Here also I'll keep this constant outside the bracket and differentiate these two terms using product rule. So when you differentiate this using product rule, you'll keep this silent first and then differentiate this. So it will be u2 v m minus 2 plus 1. m minus 2 plus 1 will be m minus 1. So it is u2 v m minus 1. We just check u2 v m minus 1. Similarly, when you differentiate this, keeping this silent, you'll get u3 vm minus 2. u3 vm minus 2. So similarly, you'll keep on differentiating each term, okay, etc. Yeah, here when you differentiate this, no, mcr minus 1, I'm keeping this outside. Okay, I'm differentiating this using product rule. So that will be ur minus 1 into vm minus r plus 1 plus 1. That will be plus 2. So it is ur minus 1 vm minus r plus 2. ur minus 1 vm minus r plus 2. So now keeping this silent and differentiating this, you have ur minus 1 plus 1 vm minus r plus 1. So that will be ur vm minus r plus 1. ur vm minus r plus 1. Similarly, the next term, I'm keeping this constant outside the bracket and differentiating this using the product rule once again. So it is ur vm minus r plus 1 plus ur plus 1 vm minus r. So the same thing I have written it here. ur vm minus r plus 1 plus ur plus 1 vm minus r plus so on. This one mcm minus 1 um minus 1 v1. So keeping this outside, we have um minus 1 v2 plus um v1. So that is what I have written it here. Okay. Similarly, differentiating the last term using the product rule, I have mcm um v1 plus plus 1 v. That's it. Yeah, this is the thing here. Okay. So this is all about differentiating. Step 2 once again, we'll be getting uvm plus 1. Okay, let's move on to next step. See here in this step, what I've done is I've taken this. See here in this term and this term, what is common? u1 vm is common. So I have taken that outside. u1 vm, I have taken that outside and I have written as, see, if you take this term common, then you will be left with 1 plus mc1. Then in these two terms, you have u2 vm minus 1 common. So if you take these two common, in this term you'll be left with mc1, and in this term you'll be left with mc2. Okay, see, that is what I have written it here. Sorry, see here. First term I have written it as it is, this one, uvm plus 1, I have written it as it is. Here it is. And next in these two, u1 vm is common. I've taken that outside. Sorry. Yeah, I've taken that outside here. So here when I take that outside, I'll be left with 1. So I have written that 1 here. And if I take that u1 vm outside here, I'll be left with mc1. So I have written that mc1 here. Okay. Next plus u2 vm minus 1, u2 vm minus 1. That is common in these two terms. Okay. If I take these two terms outside, I'll be left with mc1 here, and here I'll be left with mc2. So that is what I have written here, u2 vm minus 1 into mc1 plus mc2 plus etc. up to, okay, see here, in these two terms. In these two terms, I have ur vm minus r plus 1 common. So I have taken that outside and I have written mcr minus 1 plus mcr inside the bracket. So this is what I have done here. So in these two terms, this was common. So I have taken that outside and written these two terms inside the bracket. Similarly, similarly, in these two terms, what is common? In these two terms, v1 is common in these two terms. v1 is common, and if I take that outside, I'll be left with mcm minus 1 plus mcm plus mcm um plus 1 v. I'll be left with this last. Okay, so this is mcm um plus 1v is the last term that I have written it here. Okay, and also I know the formula. mcr minus 1 plus mcr is equal to m plus 1cr. Okay, so that is equal to, see here, I've just written all that here. See, the first time I have written it as it is. See, and the second term, I can write this as mc naught. See, I can just replace this 1 by mc naught. What is mc naught? It is m factorial by 0 factorial into m minus 0 factorial. So m minus 0 factorial is nothing but m factorial, and 0 factorial is 1. In numerator will be having m factorial, and in denominator also will be having m factorial. That is nothing but 1. So I am replacing this 1 by mc naught, so that I can use this formula for this term also. Okay, so mc naught plus mc1 using this formula will be m plus 1c1. So here I have written that m plus 1c1, okay, into u1 vm, into u1 vm. Okay, next plus u2 vm minus 1 into using this formula here in this mc1 plus mc2, you will get m plus 1c2. See here, m plus 1c2. So here it is m plus 1c2 into u2 vm minus 1 plus so on, plus this one. This will become m plus 1cr using this. See, mcr minus 1 plus mcr is equal to m plus 1cr into ur vm minus r plus 1. Okay, plus etc. Here if you use that, you will have m plus 1cm. So that is what I have written here, and the term left out here with this is umv1. I have written that here, and the last term MCM UM plus 1 V. MCM UM plus 1 V. So here actually we have added the result. Okay. See here you can just compare this. This is what we wanted to prove here. So this is what we have got. Okay. Yeah. Sorry. This we have proved for M plus 1, right? Yeah, it's here. Yeah. This is what we have proved. Okay. One extra term that we are having is MCM UM plus 1 V. Okay. Here. MCM MCM UM plus 1 V. And you know that MCM is nothing but 1. M factorial by M factorial into M minus M factorial, that is 0 factorial, you get 1. So this will tally with this. So we have proved this result. So step 3 also we have proved. What is that? We have proved that the result is true for n equal to n plus 1. Okay. So this is all about the induction. So we will conclude finally, therefore, by the principle of mathematical induction, if the result is true for n equal to m, then it is true for n equal to m plus 1 also. See, in step 2, we have assumed that the result is true for n equal to m. And in step 3, what we have done is we have proved that the result is true for the next number also. So, we'll conclude that it is true for all natural numbers. So, it is true for all natural numbers. So that the statement is proved by principle of mathematical induction. Next, moving on to the example, we'll take one example how it is working. Okay, see here. Yeah, if y is equal to x square minus 1 whole power n, then prove that x square minus 1 into yn plus 2 plus 2x yn plus 1 minus n into n plus 1 into yn is equal to 0. See here, it was, see, actually in this what we have to prove, you are having the terms of yn plus 2. That is, you need to differentiate this twice and then take its nth derivative. See, if you directly take its nth derivative, you will get yn, that's it. But we want yn plus 2. So how will you get this? See, if there are see this term, how will you get this term yn plus 1? If this prove that has only this term and not this term, then we would have just differentiated this once and taken its nth derivative using Leibnitz theorem. But here you are having this also yn plus 2. So you need to differentiate this twice and then take its nth derivative using Leibnitz theorem. So here, yes, see here, if y is equal to x square minus 1 whole power n, then we have to prove this. What I'll do is, I just differentiate this with respect to x. So I'll get y1. Again, differentiating that, we'll get y2. See, when you differentiate this with respect to x, y is equal to x square minus 1 whole power n, you will get y1 is equal to, differentiation of this is n into x square minus 1 whole power n minus 1 into differentiation of x square minus 1 is 2x. And see here, splitting this term, x square minus 1 whole power, using the law of indices, x square minus 1 whole power n minus 1 will be x square minus 1 whole power n into x square minus 1 whole power minus 1. So that is what I have done. I just use the law of indices. So it is n into x square minus 1 whole power n into x square minus 1 whole power minus 1 and into 2x. I have written this n 2x as it is. I have just split this term using the law of indices. Now written like this. And x square minus 1 whole power minus 1 is nothing but divided by x square minus 1 whole power plus 1. So y1 is equal to n into x square minus 1 whole power n divided by x square minus 1 into 2x. Okay. So when you cross multiply this, you get x square minus 1 into y1 equal to n into x square minus 1 whole power n into 2x. So here this is nothing but y actually. x square minus 1 whole power n is nothing but y. So I have replaced this x square minus 1 whole power n by y. So 2x into n into y. This is what I have got. Okay. So I need to differentiate this once again, as I need y2. I'm not sufficient this with this y1. I need this term. So I need to differentiate this once again so that I'll get y2, and then I'll take its nth derivative so that I'll be getting yn plus 2. Okay, so when you differentiate this once again with respect to x, you need to use the product rule here. See, what I've done is, in first term I've kept this silent and differentiated this y1 so that I'll get y2, plus here in the second time I have kept this silent y1 and differentiated this x squared minus 1, so that will be 2x equal to, here also I have used the product rule. See here, x, there is x here, and y, it's also a function of x, so I have used the product rule for these two terms, and 2 into n is a constant, I kept that outside. So x into y1 plus y into derivative of x is 1. So x square minus 1 into y2 plus 2x y1 is equal to, we just split these two terms, 2nx y1 plus 2n1. So I have just expanded this bracket. Okay, going to next step. See here, I've taken that 2nx y1 plus 2ny onto the LHS part. So on taking this to LHS part and rewriting that, I'll be getting x square minus 1 into y2 plus 2x y1 minus 2nx y1 minus 2ny is equal to 0. And you can just see here, in these two terms, 2 is common, x is common, y1 is also common. So I have taken that term outside, and the left out term is 1 minus n. I have written that here. Okay, and differentiating this n times using Leibnitz theorem. See here, when you differentiate this with the Leibniz theorem n times, you'll get 2 plus n. Okay, so we need that only. See, with before starting up with the problem, you just need to view what is that we have to prove here. So it is yn plus 2. So we have taken second derivative and then using Leibniz theorem for differentiating that n times. Okay. So here I have arrived at y2. So now I am differentiating this above n times using Leibniz theorem. So using Leibniz theorem, see, this is one function and this is one function. So you consider this as u and this as v. Okay. So using that Leibniz theorem, you have nc naught because you are differentiating n times. So it is nc naught x square minus 1 y2 plus n. It was uvn, right? So uvn is u means it is kept as it is. Vn means I'm differentiating this n times. So it is yn plus 2 plus, next term is nc1 u1 vn minus 1. So here you need to differentiate this one time. So it is 2x, and here it is vn minus 1. So here you need to decrease this by 1. So it is yn plus 1. Okay. Next is nc2. The next term nc2, and differentiating this you'll have 2, and again when you decrease this by 1 you have yn. Okay, see, there is no next term. If you write next term, no, nc3 and differentiate that will vanish. Okay, so I have stopped it here. Plus I'll just differentiate this n times now. This first term is done. So we'll differentiate this second term n times. So 1 minus en is constant. I've kept it here. Okay, and 2 is also common. I've kept it here. The first term is nc naught. Okay, see, I'll treat this x as u and y1 as v, so that we'll have uvn will be x y n plus 1. Same thing as we did this. We'll continue 1 plus next term is nc1. See here also I've kept this 1 minus n into 2 outside, and differentiating this x you have 1, and again by decreasing this by 1 you have yn. Okay, so you just need to this one integrate that. Minus nc naught is the next term. See here what I've done is I've just differentiated this. Next term will be nc naught. Okay, one second. Yeah, when you differentiate this, no, actually here in this step you have differentiated this x, so you have 1 here. See, when you differentiate that once again, you have 0. So there is no nc2 here. So directly we have done this minus nc naught. For this next term we are finding the n. Okay, see here, derivative of x is 1. In next term it will be 0. So we'll stop for nc naught. Okay, next term is nc naught to n, and the antiderivative of this, that is y. There is only one term here. Okay, so yn, that's it, equal to 0. So when you there is only no writing next term, because you will be getting for nc1 the coefficient of nc1 will be 2 into n into derivative 1 is 0, so there it vanishes. So nc naught 2n yn is equal to 0. So this is all about using Leibnitz theorem. This is how you have to use Leibnitz theorem. And see here, in this step I have just written the values of this combination nc naught, nc1, nc2. So that is what I have written here. Nc naught is 1, so, and nc1 is n, because it is n factorial by n minus 1 factorial into 1 factorial. 1 factorial is 1, and in numerator instead of n factorial I can write that as n into n minus 1 factorial. So in that numerator and denominator you have n minus 1 factorial, you can cancel that n minus 1 factorial, and the remaining thing is n. So I have written that n here, 2x yn plus 1 plus same thing we have to do, n into n minus 1 divided by 2. Using that combination definition, you will get this, n into n minus 1 divided by 2 into 2 yn plus, here also I just substitute this value of nc naught as 1 and nc1 as n here, and again here nc naught as 1. So this is what you'll get after using the values of this combination nc naught, nc1, nc2. This is what you'll get. And in next step I've just written this x1 minus 1 yn plus 2 plus 2x yn plus 1. See here this yn plus 1, I'm just choosing this yn plus 1. Here also you have yn plus 1, here also you have yn plus 1. So I'm taking these two terms. Okay, I'm just taking this yn plus 1 terms. In these two terms you have 2 common, x common, and yn plus 1 common. So I've taken that outside. And in this, if you take 2x yn plus 1 outside, you'll be left with n. And here if you take 2x yn plus 1, you'll be left with 1 minus n. Okay, so this minus n plus n will get answered. Okay, we'll do that in next step. Plus here where is yn terms? Here you have yn term, here you have yn term, and here also you are having yn term. See, I'll just take all these 3 terms. See, before taking that, you have 2 here and 2 here, you can cancel that and take. So in all these 3 terms you have n into yn common, so I have taken that common. And when you cancel this 2, no, you will be left with n minus 1. So I have written that here. And here in the second term, when you take n by n outside, you will be left with 2 into 1 minus n. I have written it here. And here you will be left with minus 2. Okay. See, in solving this bracket, you will get minus n minus 1. That is expanding all these terms, you'll get minus n minus 1. And here when you expand the c, n minus 1 will get cancelled and you will be left with 1. 1 into 2x yn plus 1 is 2x yn plus 1 plus n y n into minus n minus 1 equal to 0. If you take this minus outside, see in both the terms you are having minus. If you take the minus outside, you'll be left with n into n plus 1 into 1. So this is what we need to prove here. See. So this result we have proved that using Leibniz here. Okay. Thank you.